Hello everyone. Today we'll talk about the solution of the problem permutation in string. We have to decide if one of the strings that we're given contains the other or a permutation of the other as a contiguous substring. Okay, so a natural first step to solving this problem is to solve a simpler problem which just asks us, given two strings, is one string a permutation of the other? So what do we know about a permutation? Well, a permutation is a rearrangement of the elements of our sequence. So for two strings to be permutations of each other, because of course it goes both ways, one is just the other with maybe some letters having their places swapped. So the probably two most intuitive ways of checking if two strings are a permutation, so if one is just a reordering of the other, would be to either reorder them in the same predictable way to some canonical form, and a very natural canonical form is a sorted form. So the first way of checking if two are permutations is just sort both, and either they are equal when after sorting or they're not equal after sorting, and that allows us to decide if one is a permutation of the other. And what do we essentially do when we sort them and we pay for it probably a bit too much? We just check how many times every letter appears in both letters. Because after sorting, we first get the A's, then the B's, then the C's. We have to have exactly the same number of all of those letters. So the other way is to count letters. And now how do we use one of those methods to solve our problem? Well, sorting seems pretty suspect, because we want to be using a sorted version of a substring. Well, that doesn't sound very nice, because we will rearrange the letters in a substring, and then we want to check another substring, so we would have to put them in place, and also for every substring we would pay the n log n cost of sorting, so that's probably not the good avenue. And what about counting letters? Well, of course, a naive solution again would count the letters of every substring of appropriate length, which would be a quadratic solution. But we can easily notice that in the quadratic solution, so we first see if this substring here is okay, is a permutation of the string that we're given here. So we count all the letters within it. And maybe it is, maybe it isn't, but if it isn't, we have to check some other substring, so maybe the next substring. So we remove this letter. And now, what do we do now? Do we count all the letters again? Well, we see that there is a lot of wasted work going on here. We can just subtract an occurrence of this letter, add an occurrence of this letter, and we have counted the letters of this shifted by one contiguous substring. So that's nice. We can get the count of letters of every possible substring of the appropriate length essentially in linear time by just going a single time over the second string. And how do we compare quickly with the count of letters in our pattern? Well, if we don't mind paying the cost of the size of the alphabet, we can just at every step walk through every letter and see if the counts of that letter are equal in both strings. So in that case we would have time linear, so proportional to the size of the string, so essentially to the sizes of both the strings. And then also we would have to pay that cost 26 times for every letter of the alphabet. And a probably faster and simpler solution, well, maybe not simpler, but faster, it's pretty intuitive, is instead of after every change in the count of letters in our substring, checking again for every letter if it's okay. Well, the only thing that could change and change the number of letters where there is a mismatch in the number of occurrences is this letter has got its number of occurrences reduced by 1 and this increased by 1 in our pattern. So only those two letters have to be checked. So in other words, we can maintain the number of letters where there is a mismatch with their count, and whenever we change this count of a substring, we can adjust the count for this left letter, this right letter. Some of them may either have been 0 and now become non-zero, which is bad for us, or may have been non-zero and become zero, the difference, I mean. And this is good for us, and we just maintain the number of letters where there is a non-zero difference between the counts in our pattern and the counts in our substring. And this is the solution that I've implemented here. We first create a counter using all the letters from our pattern. We know, of course, that the substrings that we're looking at will be of length the same as our pattern, and we want the differences between the occurrences to be all equal to 0, and at first every letter that has a non-zero occurrence in the pattern is a bad letter, so the length of the keys, so the number of letters that appeared in the different letters in S1 is the number of bad letters that we currently have. And now whenever we see a character C, and you want to change its number of occurrences by D, which would be +1 or -1, we'll do it like this. We will just take the target of C and add D to it. But before doing that, we see if the difference in the number of occurrences was 0. In that case, we have now created a bad letter. And again, if after our operation the number of occurrences becomes 0, then there is exactly the same number of occurrences in the pattern and in the substring. So we have gotten rid of one bad letter. And since this is an integer, we have to use non-local here to get access to it. It's not a problem for something that's based on reference like this counter that we use as target. So this is the procedure for updating the value, updating the count for a given letter. So we go through all the letters in our second string, and we remove an occurrence of the letter to the right, because again we're maintaining differences in the number of occurrences of letters. So the letters that occur in the pattern are taken as positive in this constructor of counter. So the letters that we have in our substring will be negative, so that the differences become 0. So we get this next letter, subtract 1 from its number of occurrences. If there is a letter here to remove, we also have to remove it. So if I minus L is a valid index, we go back L elements and we remove the occurrence of the element at that position. And if at any point the number of bad letters becomes 0, we have found a substring that contains a permutation of our pattern. Otherwise, we've checked all the valid substrings, so we can return false.